This is Michelle Tomchuk, and hopefully I can make this data summary as clear as possible. For most of the devices, most of the data here, we have this device configuration. We're running current from I+ to I- through this whole main channel, and then we have these 4-terminal voltage leads from which we can measure 4-terminal voltage, 4-terminal conductance of both this confined wire section where we create little barriers and this open wire section. So the conductance of the confined wire section, you can see here is a function of the side gate. At 0 field, we see conductance peaks, which then split at higher fields. And then in this open wire conduction, we just see the superconducting peak. And then I want to point out that when the confined wire is mostly insulating these purple regions, we do see some artifacts in the conductance of this section. So for the most part, these line cuts, we're trying to look at these higher side gate regions where this one is more conducting. So looking at the line cut from -9 to +9 Tesla, the fractionalized change in conductance is shown here, and we just see that at 50 millikelvin, we just have this very sharp superconducting peak. So looking at the temperature dependence here, we have both the 50 millikelvin data and some higher 500 to 900 millikelvin data. These higher data ones are all plotted on the same color scale. And then down here on the bottom left, we have all of these fractionalized change in conductance plots and the same ones. So you can see the superconducting compared to the higher temperature, and then just a zoom in on the higher temperature to see the temperature dependence of the feature. And most of the devices in this fridge, the fridge is really only consistently stable up to about 900 millikelvin, but we were able to get a 2 Kelvin data set with one of these devices, and we still see this feature. And so then we went to a different fridge, and we were able, so in this case, in this fridge, the field range is only ±3 Tesla. But here we go from 2 Kelvin, we still see this feature, and then up to 10 Kelvin. In this other fridge, we also have a rotator, so we can rotate the field where theta is with respect to the in-plane field, and the in-plane field is also in the direction of the current. So this device is just a simple Hall bar. So we have from an out-of-plane field to an in-plane field, we fit it to just a simple Lorentzian to extract a width value, and so we can see the width change with the rotation angle. And then we also took this data and we plotted it versus the in-plane component of the field and the out-of-plane component of the field. And then we also did a backgate dependence measurement. So from -1.5 volt backgate to 3 volt backgate. And since this was a Hall bar, we also have a Hall measurement from which we can extract a carrier density. So then going back to the original confined wire and open wire structure in that first fridge, so these data sets are all -9 to +9 Tesla and done at about 900 millikelvin. We see that this feature is very robust. We see it in most devices. And so these 10 devices here are ordered from most negative backgate to most positive backgate, because most of the so the devices, when we cool down, the as cooled down state varies from device to device, so we usually apply some type of backgate. And then the last couple slides are just these same 10 devices, but including this the conductance plot of this confined wire structure, so you can sort of see where in the confined wire structure, where in this like side gate map you are. Oops. So like how conducting it is. And so all these confined wire structure plots are plotted on the same color scale. So you can sort of compare, for example, here you see that this one is much more insulating in this region, so you have all this noise. Okay, thanks.